Let's analyze the mathematical model of our ideal capacitor. So our mathematical model for a capacitor with passive sign convention is the current flowing to the capacitor is the capacitance times the rate the voltage across it changes with time. So that means that if we have a DC voltage does not change with time. So that means the voltage across the capacitor can't change with time. So our dV dt is going to be equal to 0. So that means that at DC, the current flowing to the capacitor must be equal to 0, or it's an open circuit, just like it looks like. So at DC, a capacitor is an open circuit. If we have a sudden jump in voltage, like we turn the switch on to suddenly apply a voltage source across the capacitor, well, that would make that dV dt, that rate that voltage is trying to change in time, approach infinity. So if our current then is going to approach infinity, or take all the current, so it's going to then look like a short circuit. So the boundary conditions of our capacitor is when we try to suddenly change the voltage across the capacitor, or at very high frequency, a capacitor looks like a short circuit. At very low frequency, or DC, our capacitor looks like an open circuit. The problem with the short circuit is infinite power is not possible. So if we have our current approaching infinity, that short circuit, infinite power is not possible. So the voltage cannot change in 0 time. We can't do that. We can't get infinite current to flow through there. So the key here is that that dV dt can't approach infinity, so the voltage can't change in 0 time. However, the boundary conditions, the DC condition, very low frequency, capacitor behaves like an open circuit. Very high frequency, it behaves like a short circuit. So that's the dV dt, the derivative relationship of our current voltage relationship in the capacitor. Let's look at the integral relationship. So if IC is equal to C dV dt, then dV is equal to 1 over C IC of t, right? That's just of t. IC is a function of time dt. So what we end up with then is an integral relationship to get the voltage. So when we're looking at the integral relationship, we can look at a definite integral, an indefinite integral, or a definite integral where we define that v of negative infinity to be equal to 0 if we go from negative infinity to time. So in our definite integral, then we have the voltage is still, well, it's always 1 over c integral of I dt. The definite integral means we know that initial time, at that initial time, what that initial voltage is. So we have to add that back in. That's like our constant of integration is known. Our indefinite integral, we don't know the constant of integration, so we just call it some k. However, if we know we're starting from very, very long ago in time, that voltage at that time, that negative infinity, is equal to 0, then we can just go from t, well, negative infinity to t of I dt. So these are our three forms of our voltage, our current, the integral of our current relationship to the voltage across the capacitor. So we have to know which one to use. We'll frequently be using this one here, but we have to know which one to use. So if we're relating current to the charge on the capacitor plates, since the integral of current over any period of time is the charge accumulated, right? So our voltage then is, our charge is integral of I dt. One charge divided by capacitance, that's what our voltage is. So as discussed in physics, Q is equal to CV. And again, we're just using Q as a function of time. We're emphasizing the fact that now when we're talking about capacitors and inductors later, that when things happen interestingly across the capacitor inductor, that's when things are changing with time. So our Q of t is instantaneous charge on the plates at that time t. V of t, instantaneous voltage across the plates at that time t. So if we wanted to, for example, find the voltage, or find the capacitor voltage that's associated with the current graphically shown here, we want to create just a graph of that. Well, what we have to evaluate then is the voltage is equal to the integral of I dt. So when we're talking about an integral, we're talking about the area under the curve. So we can analyze this by analyzing just the area under this curve, or we can break this up. If we look at our capacitor or current function, it's a piecewise function. At t less than 0, it's equal to 0. From t is equal to 0 to 2, it's equal to 20 milliamps. And at t greater than 2, it's equal to 0 again. And again, that's 2 milliseconds. So at t less than 0, if the current's equal to 0, then our voltage is going to be equal to 0. If we look at, we'll do a 1 here, and a 2 here, and a 3 here. Well, what's the current going to be at, for example, at 0.5 milliseconds or 500 microseconds? It's basically going to be this area under the curve here. So if we put in a 0.5 here, that area under the curve plus the initial, which was 0, so that area under this curve is 0.5 milliseconds times 20. So 0.5 times 20 is 10. So we get 10 milliseconds, right? But then we'd have to do 1 over 5 microfarads. So at we can just what's that going to be then? It's going to be at so our 1 over c, that's going to be 10 to the 6th divided by 5, right, per farad. And then if we're just integrating from 0 to 0.5 milliseconds of 20 milliamp dt, we're going to get 10 times 10 to the negative 6 times 10 to the 6 divided by 5. So we're going to end up with just 2, right? So we're going to get up with 2 here. If we go to 1, we're basically doubling that, and we're going to end up with 4. So that's a 4. If we go all the way to 2, we're doubling that again, and we're going to end up with 8. So this is going to be linear, right? And we're going to end up with our 8 volts at, we were supposed to go all the way, yeah, at 2, right? At 2. Well, what happens then at 3? At 3 we have 0, but we have to add back in our VCT of 0, so or at 2.1. So we're going to end up leveling off. So that's the adding back in the constant of integration. We're adding up all the contributions. So all the contributions to the voltage, once it's completely charged, we don't lose that voltage, it stays there. So we could analyze that just graphically, or we could, take it and break it up into its interval, break up the integral into its intervals. At t less than 0, we said it's equal to 0. From 0 to 2 milliseconds is 20 milliamps. At t less than, that should be t greater than 2 milliseconds. T greater than 2 milliseconds, that's greater, it's equal to 0 again. So at t less than 0, we just get 0, but from 0 to 2 milliseconds, we're still evaluating our integral from 0, but not to 2 milliseconds. We're evaluating it to t because we want that function in terms of time. We don't just want to end up with what it is at 2 milliseconds. We don't want to accumulate it all. And then our v of 0 then, we go back up here, that v of 0 was just equal to 0. So we end up with our 20 times 10 to the negative 3 divided by 10 to the negative 6. So we end up with our 4 times 10 to the 3, or 4,000 t. So at 1 millisecond, that's 4 times 10 to the 3, or here at t is equal to 1 millisecond, then we get 4,000 times 10 to the negative 3 seconds, or 4 volts, just like we found. When we're at t greater than 2 milliseconds, now we're evaluating from are from 2 milliseconds to, again, to some time t. We're not evaluating to infinity, but we're evaluating to some time t. And then again, it's 0, but we have to add back in v of 2 milliseconds. Well, where do we get v of 2 milliseconds? We get it from here. So v of 2 milliseconds, we're using this function up here is equal to 4,000 times 2. Oops, that's 4,000. 4,000 times 2 times 10 to the negative 3. We'll just do 4 times 10 to the 3. 4 times 10 cubed times 2 times 10 to the negative 3, or it's equal to 8 volts. And that's what we show here. So we can get that graph, get the same graph either way. All right, we'll look at more examples of this in class.